Hello, in my Lab 5, I analyzed the motion of a collision between two pool balls. The purpose for this lab was to determine if the collision between two pool balls is an accurate representation of the conservation of momentum as well as the conservation of kinetic energy. There were three main physics ideas discussed in this lab. The first, Newton's second law, states that the final velocity is equal to the initial velocity plus the net force divided by the mass times the change in time. Second, the energy principle states that the change in total energy is equal to the change in kinetic energy, which is itself is equal to the work acted upon the system. Third, we have the elastic collision, which occurs when the initial kinetic energy of the system is equal to the final kinetic energy of the system. In this way, we say that energy is said to be conserved. I found that the observed motion does not accurately reflect the conservation of momentum and energy, although the model motion does. Here's the observed tracker motion. The ball on the left is referenced as ball 1, and the ball on the right is referenced as ball 2. I mainly focused on x position data points, as I assumed one-dimensional motion in this system. I found the mass of each pool ball to be 0.16 kilograms. Pool ball diameter, which was used for the calibration stick in the tracker analysis, was found to be 0.114 meters. The initial position of ball 1 was found to be negative 0.001 meters. The initial position of ball 2 was found to be 0.584 meters. I found the ball 1 initial velocity by using the first two data points in the tracker observation, and I found this to be 2.545 meters per second. The ball 2 initial velocity, since it's not moving, is 0 meters per second. In order to construct the code, I first had to find final velocities for balls 1 and 2. To do this, I utilized the conservation of momentum equation for head-on elastic collisions, which states that the mass times the initial velocity of the object 1 is equal to the mass times the final velocity of the object 1 plus mass times the final velocity of object 2. Ideally, the ball 1 would be at rest following the collision, so the final velocity of ball 1 would be 0. Since ball 1 is at rest, ball 2 would have to have the same final velocity as the initial velocity of the ball 1 in order for momentum and kinetic energy to be conserved. I also added a few lines of code to allow the model to determine when exactly a collision would occur. To do this, I first had to assume that a collision would occur when the distance between the two balls' centers was less than or equal to double the radius of one of the balls. I created an if-else statement to model a collision if the distance between the center of the balls was less than or equal to 0.114 meters, or twice the radius of the two balls. I included the distance equation itself to allow for the code to formulate the distance, and I included the final velocity equations in terms of the ball 1 initial velocity. I also edited the calculation loop to include Newton's second law for finding both final velocity and final positions. Here's the model. The blue represents ball 1 and the red represents ball 2. In order to compare predicted and observed motion, I compared the observed position versus time through tracker and the predicted velocity versus time printed off in the code. In the position versus time data, you can see that there's not a straight line in ball 1 or ball 2, meaning the velocity is not constant throughout. There's also some movement in the position of ball 1 after the collision, which is not expected in elastic collision. In contrast, the velocity versus time graph shows constant velocity, initially in ball 1 up until the collision, and then in ball 2 throughout the rest of the experiment. When comparing values between the observed and predicted motion, we see a much larger difference than what's seen on the graph. The change in velocity I found by subtracting the initial velocity of ball 1 from the final velocity of ball 2. In the predicted motion, since both velocities are equal to 2.545 meters per second, I found the change in velocity equal to 0 meters per second. In the observed motion, however, the final velocity is much larger than the initial velocity, so the change in velocity is equal to 1.575 meters per second. As the velocity changes for the observed motion, the momentum also changes, and the change in momentum is equal to 0.252 kilograms times meters per second, while in the predicted motion, the change in momentum is equal to 0 kilograms times meters per second. Lastly, kinetic energy, which is equal to 1/2 mass times the velocity squared. The change in kinetic energy is equal to 0 joules for the predicted motion, while in the observed motion, the change in kinetic energy is equal to 0.840 joules. In conclusion, I'll reiterate that the observed data does not seem to show the conservation of kinetic energy nor the conservation of momentum, although the model data seems to. There were a couple of potential errors in this lab. For one, I chose to focus solely on one-dimensional motion, ignoring the y component due to the fact that I couldn't really see it with the camera angle that I had chosen. Had I have had more time to focus on a different camera angle, I could have observed Y position that could have affected the velocities in my observed data. In addition, I could have plotted incorrectly on the tracker data, thus altering the velocities as well. Thanks for watching.